3, 2, 1, go. We are live. This is Retraice segment number 85 for Saturday, December 17th, 2022 at 10 p.m. Eastern, 7 p.m. Pacific. Retraice is about what's going on out there. The short answer to that is computer control. The long answer to that is natural, artificial, and strategic intelligence. And Retraice is for outsiders. But we came to the conclusion that the computer control game is player-oriented, and outsiders are not players, so here we are. What are we doing? We're working on AIMA4e, the math and the code. We're in the December to Remember math and code event, and we're in the middle of trying to implement best first search, which takes the argument, one of its arguments is problem, and we don't know how to do that, or we didn't when we started. Now we're getting closer and closer. Today was supposed to be expanding a node. What the heck am I talking about? Expanding a node. Why don't you expand on that, expanding a node? So this is our map. This is a graph of the state space. We're trying to get from A to B, trying to travel across Romania, and we don't have an airport. We never built it. We just did the math and decided not to build the airport, so we're going to have to drive. If we want to get from A to B, we can use our human brains, but what if there are a lot more cities, or what if we just don't want to use our brains? We're going to need an algorithm. Best first search is one that we can use, but we have to formulate the problem of getting from A to B in a way that the computer can understand, and that is the code in the math and code December to Remember part of what we're doing, or that's the code part. That's why we're doing what we're doing. So today was supposed to be expanding a node. Again, I didn't explain what expanding a node is. So this is the state space. Okay, these are all the different states that we can be in. We can, in our little vehicle, because we're not walking, are we? Come on, we're further along in civilization than that. We start out at this initial state, and then we have to use our best first search program to decide where to go next, and then where to go next, and then, and actually, before we actually go anywhere, we are going to just search. This is a search problem. We're doing a search of this. So there's the state space and then the search tree. So we're trying to build a search tree before we even put pedal to the metal to get to Bucharesti. We want to build a search tree and find the best path according to some algorithm, best first search. There are other algorithms that we can use. And so we need to build that search tree. What that means is, so we'll create a node in our search tree that corresponds to this state in the state space, and search trees are going to end up looking like this. Here's the first step in the search tree. We expand this node, and then we get these new child nodes. This becomes the parent node, and we do it again. This one has only one child. This is a one-child policy. This is a two-child, and this is a one-child policy, if you know anything about China. And then we keep going until we reach B, Bucharesti. And then once we know the shortest path based on or the best path according to the particular algorithm we use to build this search tree over this state space, then we can put pedal to the metal and get to where we're going. And whatever's in Bucharesti, we got to get there quick. It's going to be awesome. Okay, so expanding a node, going from just initial state to, a frontier of 3 nodes, a reached space of all of these. I think the reached space is defined as the frontier plus this is called a certain kind of boundary, and I forget what it's called. But anyway, we're not doing the AI stuff. That's another thing to remember. We're not really trying to learn the AI. We're just trying to learn enough right now in December to Remember Math and Code event to code, do all the coding that we're going to need to do to understand the AI. So that's what we're doing. Okay, so expanding a node, that's what we were supposed to do. Didn't do it. Why? Okay, so first of all, we've talked about implementing the class problem in Python. We've talked about implementing nodes as classes in Python. And no, that spoiled it. Don't show these things. Oh, okay. So where's the expand? Okay, I got to leave that there because I'm going to be looking for that. Let's duplicate this tab. And that didn't help at all. Okay, so let's do Command F, expand. There. Okay. So this is what I was planning on doing today until I got into it and realized there were some dependencies that I hadn't satisfied. Not software dependencies, but, software dependencies. I mean, yeah, like just not from outsiders, but from our own implementation. So this is, this is what we did yesterday. This part here, highlighting is no good. These are a couple of nodes that they define to keep the algorithms from getting stuck. So the failure node takes as its argument the state of failure, And so this is an instantiation of the class node. This is a node called failure, and its state is set equal to failure. Its path cost is set equal to math.infinite, and I think that just represents an infinite number using the math module or math package. Similarly, we have a node, a cutoff node. So these are not. So remember, our state space, it has, is sort of the real world we care about, but our nodes, okay, they are abstract, and you can have two nodes corresponding to a single state space depending on how you arrived at the state space. So there are two nodes that can be here if we're expanding a search tree. We shouldn't ever find the second one. We should avoid calculating the last. Well, we'll have to calculate it to know we don't want to connect to it. But one of the nodes keeps track of this path to arrive at Sibiu, and the other node keeps track of just going straight there. So two nodes, one state space. That's an important concept to remember. There's only one state space, Sibiu. I gotta learn to pronounce that one. But there could be two nodes that correspond to it depending on how we expand our search tree. But when we're expanding things, we want to be able to cut off if the cost reaches for some reason, infinity. So we've defined a node that's not in the node that corresponds to not a state in the state space, but a state that we're going to invent in the state space called cutoff, and then another one called failure. These are just things that don't line up with states that we care about in the state space, and their ways of controlling our algorithms and our agent programs, so they don't keep going on forever or get stuck in some way. So then, that's just these two lines here. And so then what we wanted to do today was expand a node. But why can't we expand a node? Or why did I come up short on this particular ambition for today? Well, let's have a look at what happened, or some of what happened. So I should say what you're going to be looking at in the terminal now is just copy and pasted stuff from the GitHub, the AIMA GitHub source stuff that we just looked at. A little bit reformatted. I've cleaned out a lot of the comments. I lost a lot of time trying to figure out like how to sort of build consistency from day to day in a single source file, but avoid showing the comments, because the comments yesterday made sense and the day before made sense for those days, but then they become clutter, and I don't have good tools in Emacs to get rid of the kind of clutter that I'm creating. So I've just started a little bit fresh here. It's all in the GitHub, in the Retraice GitHub, and you can get to that from our website. So what you're looking at here will be there. Okay, so up here's some import stuff. Don't worry about this. This is just to, I only put this in here because I'm going to run this whole file probably, and I just wanted everything to be there, like the math module in particular, the module. Okay, so this was day one, define the class problem. Okay, day two, define the class node. This is the two special nodes that I just talked about, failure node and cutoff node. Okay, so here's our expand function. That was the plan for today. And what happened was, like in the first line, you've got the first line, or the top of the for loop in there. So first, what does it do? It takes as an argument our problem and the node that you want to expand, okay? Now, what does it do? It sets S equal to the state that corresponds to that node, okay? Remember, you can have multiple states that correspond to a single node. You can't have multiple nodes that correspond to reverse that. You can have multiple nodes that correspond to a single state. You cannot have multiple states that correspond to a single node. At least I don't think you can. I'm pretty sure you can't. It's supposed to be a unique path. Come on, get the right answer here. I'm going to read from the text, AIMA4e, page 71. The search tree may have multiple paths to, and thus multiple nodes for, any given state. But each node in the tree has a unique path back to the root, as in all trees, they say. Okay, so yeah, so each node has a unique path back to the root. That's what's unique about a node. States do not have that uniqueness, because you can, in a lot of states, you can find your way. I mean, if we look back, just to ram this home, just to beat this dead horse, Fagarash here has multiple paths back to Arad. You can go this way, the long way, the scenic route, or you can go the straight shot, as long as it's not during rush hour traffic. Okay, so that's what's going on here in, in our expand node function. So we set S equal to the state of whatever node we're at when we want to expand a node, or whatever node we want to expand. And then we have a for loop for all the actions that are in the problem actions of S, so of our node.state. So replace this S, okay, with node.state. So we fetch the state attribute from node, okay, whatever our node is, and the node isn't going to be called node. We're defining the function here, but when we call the function, we're going to we're going to do something like this. We're going to say expand AB problem. Okay, so we're using the expand function on our AB problem. Now, what am I going to call it? Well, okay, yeah, let's just call it AB problem. And then our node is let's see, I don't know, whatever it was. Okay, so that's what it's going to look like when we call this expand function, and that's what these two words up here, problem and node, correspond to. Okay, so for action in problem.actions of node.state is what you should see here. When you see this S is node, you should think node.state. So the state attribute in our node, we've passed that to the actions method in our problem, and that's defined up here. Now that's another problem. So immediately this is actually the first problem. So we have not implemented this in our class problem. We're supposed to subclass problem and make a new class for our particular kind of problem. And so this is going to raise a not implemented error. But right now, the result method on the object, let's say our object is AB problem, which is our problem object, we'll call AB problem. The result method, sorry, not the result method. What am I saying? Oh, I'm saying result. No, actions method. The actions method on, okay, so so that first method under problem corresponds to, no, I was right, result. Ooh, this is confusing, sorry. So the result method of actions on S, so it uses, goodness, I am all over the place. It is actions, I'm not a moron. I'm smart. I'm good enough. I'm smart enough, and doggone it, people like me. Okay, so the actions method, that's too old for most of you. That's good old Saturday Night Live. So the actions method applied to our problem takes the argument state. So down here, we're going to give it the argument S. Okay, that's S. We've already set that equal to the state of the node that we care about. And then it returns what? Well, right now it just raises an implementation error. What is this going to look like? What can we spoil this a little bit for ourselves? Yes. So I looked further in their source code. Oh, that's not nice. What is that? Highlight indent mode. Don't do that. Okay. What else? Am I in ELP? I'm not in. Okay. There's other things I should do. Okay. Let's look at this route problem that they define later, okay? So when they implement actions on state here, they subclass problem. Okay, that's what this means. This right here means they're subclassing problem, just like we subclassed object to create the problem class. They're subclassing problem to create the route problem class, okay? And they've redefined actions here, and what their definition of the method, their actions method does this. It returns the map.neighbors of state method on the problem. I'm struggling to explain this as the list of actions. Okay, so that'll be our list of actions. That's what it looks like down there. Okay, let's just not dig too deeply into that. Anyway, we're going to from our problem, given the state that we're in, we're going to fetch a list of actions from a dictionary, and it's going to be a dictionary, right? Are the actions a dictionary? Let's see. I can't tell. Map.neighbors. There's a lot of stuff. Oof, okay, no, we're not going to be able to resolve that. Some sort of data structure that works. And then, and for each action in that list, so this is a for loop, okay? So for each action in this dictionary lookup of the state S and looking for the actions for our problem, we're going to do this. We're going to set S1 equal to the result of applying action to state S. Okay, set S1 to the so basically what that's okay. Let's get away from the code for a second here. What it's doing is it's just basically looking up that state in the. And this is the other thing, like to define the problem, we have to define the state space and the actions that can be applied to each state and the result of those actions. Let's go to the notes. To define the problem, yes, structure of a problem. The actions on state, and this was an S, by the way, the other day I said the S, I couldn't remember if the S was supposed to be there. Actions on state function returns a finite set of actions that can be executed at state. Okay, that's the actions. But then the result, where's the result? The transition model is the result function applied to the state and the action. And so that gets us our new state S prime. So what are we looking at in our code? We are looking at the result. So first we got the list of actions, okay? This is our actions function to get the list of actions that are available on state. Then we go down here to our result function, or method on the problem. Method, it's a function, but it's inside of an object, so we call it a method. We're going to use the result method to apply that action to our starting state to find the state that will result from that action being applied to the starting state, and then we're going to set that state equal to S1, right? That's S1. The state that's the result of applying action to state, or our starting state, is state 1, is our new state, S1 or S prime in the notes. Then we need to, so we've discovered what state 1 is. And I think here is where you might get a failure node or a cutoff node if there's no, if something happens that doesn't lead you to a nice clean next state. And then here we've got to calculate the cost. So the node.pathCost, you take the path cost that you've got already from the node that you're at, and then you add the action cost of state action. So how is action cost going to be calculated? Action cost, yeah, it takes 3 arguments. Okay, so up there, action. Okay, this takes 3 arguments. And up here, it's returning 1, but let's see if in our, here, down in our route problem, it's taking 3 arguments as well. They're re-implementing it down here in the RouteProblem subclass of problem, and it's doing something much more interesting with those arguments than just returning 1. So we're going to get from this action cost in a subclass, in a real implemented subclass of problem, we're going to get an action cost that's not just 1, okay? So now let's, oops, I'm trying to be slick. I'm not so slick. There we go. Yeah, so we're back at expand problem, the expanding node function. And so until we implement a better problem with a better action cost method on it, we're just going to get back 1 no matter what we do. Okay, so that's another thing that means we can't do this interestingly today. And then we're going to do the yield, and the yield is going to generate a new node with the arguments of the new state, which is S prime or S1, the previous state, which is the previous node, and then the action that led there, and then the cost. Why? Because a node takes 4 arguments. I thought it only took 3. Node takes 4. Yeah, okay. The state, parent, action, and path cost. So state is the new state of this. The state to which this node corresponds is 1. Oh, don't do that. I don't like that. I keep doing that. Why does that happen? That's like not something I can. That's some key thing I'm doing wrong. I get never mind. I shouldn't talk about it. Okay, it's an Emacs thing. And then so our second argument is the node that we started with, which is now the parent node. Okay, so we're looking at this second argument when we're instantiating an object from the class node is supposed to be the parent node. Well, what's the parent node? It's this. It's not that. It's not the state. It's the node that we took when we first started expanding. It's the node we're trying to expand, okay? And to get the child node, we have to yield a new node based on a new state, the parent node, the action that led from the parent to the child, and the cost, which we've already set equal to this interesting stuff here, okay? And then once we've done all that, we've yielded, and this is a for loop, so we're going to do these three suites in this compound statement. We're going to do all three of those for every action that's available in our problem on the given state from our parent node or our starting node. And that's expanding a node. Okay? Now you can see, like, I can't execute this code right now, mostly, perhaps entirely, because I haven't implemented a real problem. Like, the only problem that we've done is just a toy problem with toy arguments. There's nothing interesting that's going to happen here, and I don't have. And okay, so there's more to. Okay, so let's talk. What else? It's not just like I couldn't do this quickly. I couldn't do a dummy. Like, this is what I started with. I started with st space was going to be my state space, and it doesn't have any actions. I just wanted to create a problem. Stop that. I just wanted to create a problem getting from state 1 to state 11. Just go to 11, right? And okay, what's our state space? Oh, let's just give it some random numbers. Let's make this easy. No. You got to specify actions at least, okay? And so that was our state space. That's what I wanted to do. And then our get to 11 problem was going to be an instantiation of problem given the arguments. That's my initial state. That's my goal state. And I don't think I need to. What else do I need to do? And I could do keyword arguments, but they're not necessary. Okay, so I started looking at I looked further down in that same IPy notebook for how they're implementing stuff, and I sort of annotated this best first search. Well, this is the implementation of best first search that they give, and we need to sort of, in a sense, work backward from this. So first, other than the problem not being, I shouldn't say done up here. That's not done. Okay, and we're in that. Not done. See, it doesn't auto complete with character. No, not node. Not. Ugh. Not. Jeez. No. Done. Jeez. Way to go, Slick. You're getting bells all over the place. Bells and whistles. So problem is not done. Problem is not done. And then the priority queue is another thing we're going to need to do best first search. We haven't done that yet. And then this, I think, is a straightforward problem as long as we've defined the problem. The reached dictionary is the list of reached nodes. The while loop that they're going to apply to the frontier. So I'm just going to sort of read through my comments here, starting with the first node in frontier. Frontier is going to be ordered. Remember, if you go to the pseudocode, bang, no, bang, no, bang, yes, no, yes. If you go to the pseudocode, one of the things it takes is a problem. The other one argument, and the other one is this this evaluation function. And you can see here in frontier, okay, if you look at our code, and let me just highlight front, no, not capital. Okay, so that's frontier, and then over here we see frontier is a priority queue ordered by F. Okay, so F has to put this in order. And actually, if you change F, this evaluation function, you get different algorithms. That's the way they describe it in AIMA. And node is an element. It's a list of nodes, a queue of nodes. A priority queue ordered by F with node as an element. Yeah, so you have to, whatever node you're at, you have to start with by putting it into the priority queue and see. Shut up. I'm not explaining this well, and why would I? Okay, so let's go back to the code. And so frontier needs to be implemented here. which is a priority queue, which we're not ready to do. And then we set node equal to, we pop the top item off the list of node, or off the list of frontier. If the problem is, or if the node state is the goal state, then we return that node because we're done, we've succeeded. Else, we're going to do a for loop here. I don't know why. Oh, it's while. So I don't have to, it's not if then else control structure, it's a while loop. But here we would exit out because we found the goal state, so we're done. Otherwise, we continue and we start a for loop to take, so for each thing that we're going to call child in the expansion of problem, of the node that we're at, given this problem, we're going to set S equal to the state of that child node. Then we're going to check to see if S is in reached. If it's not in reached, or if its path cost is less than the path cost of reaching it from another path. So we could be at the node, we could be in the state at the state from another path. We check to see if the path cost of the new arrival path is less than, and if either one of those is true, then we add the reach state. We add the state. This is the one I didn't know exactly how to say. I think the right way to say this is add the pair to the reached dictionary, the dictionary of reached nodes, state node pairs. And the form of the dictionary is this here. Okay, you got your state of your child node, and then you've got the, I didn't write this correctly. I should just say, this should just say child, the node shouldn't be there, but I didn't want to just write child because that's when code gets hard to understand, is when you just start using the variable name without any hints. So that adds to this reached dictionary. And so so as long as one of these two conditions is true, either it's not in the reached dictionary already, or the state is in the reached dictionary, but the cost of that state that's already there is more than the one that we just found, then we're going to add it to the dictionary, and then we're going to add the node. So we're going to add a pair to the dictionary, the state and the node to the dictionary, and then we're going to add the node to the frontier queue. Okay, and then we're going to start over when we. So this is a while loop that's dependent on going through each item in the priority queue, the frontier. Once this finishes with the existing priority queue, it's going to start over, but that priority queue is going to be newly updated by adding child nodes to that priority queue. And then if you don't get there, just return the failure node, which we defined up here. Okay. There. Okay. So that's their implementation of best first search. So there's stuff that we have to do in there, and there's some things that I've got some question marks, and I'm not sure exactly if I'm explaining it right. I think I am. But the most important stuff is problem's not done, and then priority queue is not done. So we can't implement their best first search. And so if we can't implement theirs, we can't implement our toy one unless we have something that corresponds, blah, blah, blah. Looking further ahead, we've already talked a little bit about their definition. This is their implementation of a route problem. And then also the map stuff. I'm not going to go into this right now. But there's more stuff that's, we're not there yet. We can't be sure that we know what we're doing until we can execute an agent function, an agent program with an agent function, or at least a search algorithm in the form of a function on data structures that represent the state space and the problem and yield a solution, and really the best solution based on our chosen algorithm, which is going to be based on that evaluation function. All right, I hope that wasn't too much of this and too much of that. Onward. Some days we're not going to be able to do what we want or what we set out to do, but that's why we're in December to remember. It's like these things that you think are easy, they look easy, and you miss one little thing. Oh yeah, that's right. I haven't really properly subclassed problem or defined action cost method, or I don't have a map of Romania that my program can talk to, and the toy one that I would build is almost pointless because I can just use one that already exists and adapt it into a toy problem if I want. Things expand, so you have to start to get a feel in programming. This is a constant theme. You get a better and better feel of what seems like it's going to take a short amount of time and ends up taking a long amount of time, or a large, short and long amount of time. If you've done programming, you know that. If you haven't, you don't. Okay, all references and everything and notes will be in the notes at retraice.com, retraice.com, notes.retraice.com. You can check out our GitHub code at our website as well. We can have a look. I'm just going to show you the GitHub page, and this is just what it looks like. You can just jump to the folder for today's segment if you want the code. Jump in there. Sometimes there's two versions, the clean one and the dirty one, but I'll eventually work around that. This is all the stuff we talked about. Everything above us. We didn't talk about the everything down here below. I'll comment that stuff out before I put it up, or before I do a final commit here. But that's all there, and that's it. Okay, same time tomorrow, 10 p.m. Eastern, 7 p.m. Pacific. Signing off.